So let's just move on further and talk about some of the other important questions that are totally based on the Euclid's division lemma. As we know that what is the meaning of the Euclid division lemma, that there exists any A and B, for them there exists any Q and R, such that A is equal to BQ plus of R, with the condition that the value of R should always lies in between the value 0 and B, where the equality occurs at the point 0 only, not for the B. So let's just start with some of the important questions that are based on it. So let us suppose I'm talking about the question number 1. The question number 1 says, show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus of 1, where q is some integer. So basically there are two questions in this particular one question which says that every positive even integer is of the form 2q and every positive odd integer is of the type 2q plus 1, where q is some kind of an integer. So let's just start the solution set of this particular question. As we know that we have to solve this question with the help of the Euclid's division lemma, because here we are talking about the divisibility of any particular numbers, or here we are talking about getting an even integer and an odd integer. So let's just start with it. So let us suppose I'm talking about the solution of this particular question. So I'll start with, let A and B are any positive integer. So always remember to start with any particular type of question with this, let A and B are any positive integer. Let A and B are any positive integer, and we know that we have to form the number in the form of 2q and in the form of 2q plus 1. Here the number is 2q. Let us suppose I am writing down the key points of this particular question, 2q and 2q plus of 1. So we have to form the number either in the form of 2q and either in the form of 2q plus 1. So always remember this fact, we always have to choose a number B. We always have to choose a number B. Means for any A and B are any positive integer, we have to select or we have to suppose a number B. So let if we have to form, as in this particular question, we have to form a number either of the form 2q or 2q plus 1. So I am taking the number B as 2 because 2 and 2 is common in both of these numbers. So let us suppose I am taking the number B over here as 2. So let B is equal to 2. Let B is equal to 2. So the starting of this particular solution would be like, let us suppose we have any two A and B positive integer, and we have to suppose the number B as any integer. So as per the question, we have to form the number either in the form of 2q or either in the form of 2q plus 1. And there is one thing common in between these two numbers is that there is a use of a number 2 over here and over here as well. So that is why I am taking the number B as 2. So by Euclid division, by Euclid's division lemma. So actually I'm using Euclid's division lemma over here. By Euclid's division lemma, we know that A is always is equal to BQ plus of R, where R always lies in between 0 and B. R always lies in between 0 and B. Let us suppose I'm putting it in a box. So let us suppose we are using this particular Euclid's division lemma. So as per this Euclid division lemma, we can write A and B as in this formation, as A is equal to BQ plus of R. So in place of A, it will be A again. In place of B, we can substitute this value of B in this particular formation. So B will be like 2Q plus of R, and the condition of R will be R will always lies in between 0 and B. So what is the value of B? We have taken the value of B as 2. So B is nothing but 2. So by Euclid's division lemma, we get the result as A is equal to 2Q plus of R, with the condition that the value of R is lying in between 0 and 2. The value of R is lying in between 0 and 2. Now, we know that we have the condition on R as the value of R is lying from 0 to 2. What does it mean? It means that the value of R can be 0, the value of R can be 1, but it cannot be 2 because there is no such equality over here. It means that the value of R will start from 0 and it goes till 2 but excluding 2. So it means we have the two values of R as R is equal to 0 and as R is equal to 1. Now substitute these two values in this particular equation again. So let us suppose I'm talking about this equation as 1 and this equation as 2. So we will substitute the value of R one by one in the equation number 1. So let us suppose I am taking the case 1. I am taking the case 1 as when I am taking R is equal to 0. Substitute R is equal to 0 in equation number 1. Substitute R is equal to 0 in equation number 1. So it will be like A is equal to 2Q plus of R. When I'll substitute the value of R as 0 over here, the A will be 2Q plus of 0. A will be 2Q plus of 0, which says A is equal to 2Q. Which says A is equal to 2Q. So obviously we know that we are getting the result over here as A is equal to 2Q, which means that this is nothing, or this number would be definitely an even integer because we have a multiple or we have a factor as 2 over here, and whenever any particular number do have a factor 2, then it is definitely an even integer. So it means that this number is an even integer. So it means that the part 1 in which we have to show that every positive even integer is of the form 2Q is already proven over here, because the number A that we have taken, which was any positive integer, it is now of the form 2Q, and 2Q is definitely an even integer. So the very first part of ours is proven over here that every positive even integer is of the form 2Q. Now move on to the case number 2. Now we are left with our second part, in which we have to prove that every odd positive integer is of the form 2Q plus 1. So let's just start with it. Substitute the value of R is equal to 1 in the equation number 1. So when we'll substitute R as 1 over here, so we get the answer as A is equal to 2Q plus of R. What is the value of R over here? R is nothing but 1. So we are substituting the value over here as 1. Now we know that we have the number A as 2Q plus R. We know that 2Q is nothing but an even integer, and whenever we will add a number 1 in the even integer, it always results into an odd number, because 2 plus 1 is nothing but 3 and 3 is nothing but an odd integer. 4 plus 1 is nothing but 5 and 5 is an odd integer. So it means that A is equal to 2Q plus 1, A is equal to 2Q plus 1 is nothing but an odd integer. So it means that the second portion is now all clear, or the second portion is proved over here that every positive odd integer is of the form 2Q plus 1, because in this particular questions there were two parts, in which either we have to show that we have to show that the positive even integer is of the form 2Q and the positive odd integer is of the form 2Q plus 1. So in the case number 1, we have proved that the formation of A is nothing but of the form 2Q, and 2Q is an even integer. So any positive even integer is of the form 2Q, and in the second case we have proven that A is equal to of the form 2Q plus 1 and 2Q plus 1 is nothing but an odd integer. So it means that every odd integer is of the form 2Q plus 1. I hope the solution set of this particular question is all clear to you. So let's just move on further.